So let's get started. Thanks everyone for showing up. It's very early here. It's a great pleasure to have Matteo here, who's going to give the first talk for today, and it's going to talk about offline Primal-Dual reinforcement learning for linear MDPs.
Thank you. Thanks for the introduction. And thank you for having me here in this legendary place with such a great company to talk about offline RL. So first of all, I'm going to talk about this work I've done with Gergo. I'm sure most of you know Gerge, and with two of his PhD students, Germano and Nika. And okay, first of all, this is about offline reinforcement learning. So if you're not familiar with this, let's start with an example. So let's suppose you want to train a chatbot or a virtual assistant to deal with your clients. Let's say you're a company, you have clients. In online RL, you would deploy an agent that has to learn from scratch by interacting with your clients. On the other hand, in offline RL, what you would do is to feed this agent a lot of historical data, a lot of recorded interactions to train it before deploying it with the real client. So it's easy to see that this is safer in many applications. It's often less expensive. It exploits the availability of large data sets that you have in several applications. And also does not prevent you to eventually go online and learn online. You can see offline reinforcement learning as a pre-training phase. The disadvantage, of course, is that the agent itself doesn't have any control over the data. So the data are given to the agent, and the agent has to do the best he can with the data that is given. So this is the protocol of offline reinforcement learning. An algorithm here is something that takes a data set and produces a policy that then you can deploy in the real system. And a data set is just a set of interaction samples that in practice can be generated by multiple agents or different versions of your agent over time. But for simplicity, think of the data set as being generated by a fixed behavior policy, so a single fixed agent in the past. So our goals here is to learn a policy that is close to optimal with a polynomial amount of data, and also with polynomial computational complexity. And also, we would like this algorithm to work when you have a state space that is very large or even infinite. Also, we would like it to work in infinite horizon tasks. And we would like to make weak assumptions on the agent that generated the dataset, so on the behavior policy. I will make this more formal as we go on. Let's start from formulating the problem a bit more precisely. So the agent in this setting has no access to the environment, so no interaction is happening during the learning phase, but still there is interaction in this problem. And of course, we model it with Markov decision processes. This is how the behavior policy interacted with the environment in the past. And this is also how the final policy you deploy will interact with the environment once you have learned it. Of course, you all know this, it's very standard. Just I will denote the states with X and actions with A. And we consider the discounted setting since we want to deal with infinite horizon tasks. But all of this, we will see, will extend also to the average reward setting, which is not very common in offline RL. Okay, and also there is a starting state distribution, mu0. A policy, of course, is a mapping from states to distribution over actions. We're considering stochastic policies. And the return is the sum of discounted rewards following the policy. We normalize it by 1 minus gamma here. And of course, we're interested in finding the optimal policy, that is the policy with the largest expected return. Okay, this is just for notation. We'll use this expectation under pi to mean expectation over the trajectories generated by following policy pi. Now, there are some fundamental quantities that, of course, you know about already. The state occupancy measure in the discounted setting is a discounted probability of visiting a state at some point in the interaction between the policy and environment, and it's denoted by mu pi. Mu pi is the same, but also taking actions.
Can we send you a Google Meets link to join?
Yes.
Yes.
Yeah, no worries. Okay. Information.
I sent it to your UPF account, I think.
Oh, okay. I got it. Oh, oh, sorry. Yeah.
You have to admit.
Oh, that's
Can you let me in? Yeah.
Oh, I can do that.
You're gonna be feedback.
Oh, yeah. Turn everything off. Okay. No feedback loop. Okay. Can you see this? Okay.
Full screen.
So I was telling you about occupancy measure. So nu pi is state occupancy measure, mu pi is state action occupancy measure. And yes. Yes, I can. Thank you. Okay, so once you have introduced these occupancy measures, now you can rewrite your expected return in this way, as this linear combination, or as an expectation over states and actions between your state action occupancy measure and the reward. Okay, but there is another way we can write this expected return as a linear combination, and that is with value functions. So if you have your Q function, Q, and value function V, now you can also write the expected return as linear combination between the starting state distribution and your state value function. Again, we normalize it by 1 minus gamma. This is also the expected return of your policy. And these two formulations, as we will see, are one the dual of the other. But first, I also have to tell you about how the data are generated. So we have seen there is a fixed behavior policy. And now the data set is composed of n independent samples, W, where each sample is composed of an initial state sampled from the starting state distribution, a state action pair obtained by following your behavior policy phi b, so sample from the state action occupancy measure of phi b. And then you have the corresponding reward of this state action pair and the next state sampled by the environment's transition kernel This is a bit artificial as a model of how data are generated, because basically each data point corresponds to an entire trajectory obtained by following pi_b, but it's simple to analyze, so we will use this model. So to summarize, okay, we take a data set of this form, and our algorithm will produce a policy pi out, and hopefully this the expected return of pi out will be close to the one of the optimal policy, epsilon close. And we want to achieve this with a data set of size polynomial in 1/epsilon. To do this with all our requirements, we will need, of course, some assumptions. First of all, assumptions on the quality of the data or on the quality of the behavior policy. And this brings us to the fundamental problem of offline RL, that is the distribution mismatch between the policy that generated the data and the policy you are trying to learn, the optimal policy. They may assign very different probabilities to state action pairs, and these may lead naive algorithms to overestimate the value of actions that are underrepresented in the dataset. So we need to make some assumptions on how well the behavior policy covers the space of possible decisions. And this distribution mismatch is also why pessimistic algorithms are popular in this setting, because they try to prevent this overestimation issue by actively underestimating the value of actions that are underrepresented. So a possible way to formulate this is with coverage ratios. So if you consider the ratio of occupancy measures between your behavior policy pi_b and any policy pi, okay, this ratio captures how much the behavior policy covers some policy. And now we're taking the supremum over policies. So if the behavior policy gives a small probability to a state action pair that is visited by any policy, this ratio can explode. On the other hand, if the coverage of the behavior policy is good, this ratio will be small, order of a number of states times number of actions. So assuming this ratio is bounded means the behavior policy covers well all the possible policies. This is a strong assumption that has been made in the past. For instance, the FQI algorithm, a classic batch reinforcement learning algorithm, can be shown to enjoy this epsilon to the -2 sample complexity under this uniform coverage assumption. But some algorithms, for instance, pessimistic algorithms, can achieve the same with a weaker assumption that is sometimes called partial coverage. Now, the behavior policy only needs to cover the optimal policies. And we will work with this assumption, and we will call this partial coverage ratio C star.
Sorry.
Yes.
What is the C star?
This C star will appear in the sample complexity. Sorry, what is the?
How does it appear?
So it will appear in this O epsilon to the -2 polynomial. Yeah, it will be typically it's linear when you consider sample complexity. Yeah. Okay, since we want to work with large or infinite state spaces, we also need some structural assumptions. So importantly, our algorithm computational complexity cannot depend on the size of the state space. We have to use function approximation, and we will work in the linear case. So we will work with linear MDPs and linear function approximation. So linear MDPs means you have access to a feature map, phi, that maps state action pairs to the dimensional vectors. And under this linear MDP assumption, both the reward and the transition probabilities are linear in these features. An immediate consequence of this is that the Q function for any policy is also linear in the same features. And theta will always denote the parameters of the Q function. Now, of course, we need to adapt our notion of coverage ratio to this setting, because since we have infinite states, the typical ratio summing over states and actions would not be meaningful. And so we need to use feature coverage ratio that represents how well the behavior policy covers the optimal policy, not in state action space, but in the feature space. And this takes the form of a quadratic form between features of the optimal policy, and this matrix is the covariance feature matrix under the behavior policy. So this is similar to what have been done in previous work, but this coverage ratio is actually smaller than the one that is typically considered. You can already see that here these features of optimal policy are. Yeah, there is a question.
Finish the sentence.
Okay, yeah. Here these features are decoupled. Usually they're under just one expectation over pi star, and so there is like a variance term missing in our definition.
That was my question.
Okay.
Yes, sir.
Have I answered? Okay.
What if that is not invertible?
Sorry?
And it's not invertible, like the second one. That the mean
If it's not invertible. Okay, yeah, good question. We will assume it is invertible.
if it's invertible, but it's still this thing is finite. That's possible, right? We can change that to be pseudo inverse.
Yes. Yeah. Good point. Yes. Anyway, for simplicity, let's say it is invertible, which you can have, for instance, if your feature map is not redundant, so you cannot eliminate features, and your pi b has full support. But yeah, let's just assume it's invertible for simplicity. Now, okay, if you're not familiar with this, maybe it's easier to think of the tabular setting again. This reduces to this ratio, which is not the ratio we've seen before. You have a square in the mu star on the top, so you can see also here that it is smaller than the typical notion. Okay, our aim is to scale with this now polynomial. Now, yes.
So you take an actual one?
The optimal policy may not be unique, right? Yes. So actually, this can be a comparator policy of your choice. So yeah, so you can just pick one. Yes.
So when you say that that's smaller than the quantity, is the difference this variance term that you were saying that it's missing? Like if you add the variance term, then is it equal?
Yeah. So yeah, this is exactly equal to the common notion plus a variance term that is like variance of features under the behavior policy. So an overview of the state of the art. First, in the first section of this table, you see algorithms that do not satisfy all of our requirements. For instance, FQI is a simple, efficient algorithm, but requires a uniform coverage assumption. Or you have algorithms that satisfy our requirements in the tabular case, but do not work for linear MDPs. And or for linear MDPs, but in the finite horizon setting. And if you move to a discounted setting, you have algorithms that are not efficiently implementable. Now, there are a couple of algorithms from previous literature that satisfy all of these requirements, at least for the discounted setting. but they don't have optimal sample complexity. So in this setting, optimal sample complexity in the sense of minimax optimality is epsilon to the -2. Previous algorithms for linear discounted MDPs with partial coverage at epsilon to the -5. Our algorithm improves this a bit. It's epsilon to the -4. It's also more efficient computationally, maybe we'll see later. And also, it easily generalizes to the average reward setting. And as far as we know, this is the first algorithm to do so. And it does so remarkably simple, just with a small modification to the algorithm. Yes?
For the average reward setting, do you still get epsilon to the -4?
Yes. Still epsilon to the -4. Yeah.
And but these other results are recorded for the discounted set.
Yes. So
the other rates.
these other rates, yes, none of these previous works apply to the average reward setting. Yeah. Yes.
This is also for finite state action space.
No, for linear MDPs, okay, you need the finite actions to implement the algorithm. It can work with the infinite states. The bounds are for linear MDPs.
In space case, you don't necessarily see any conditions, say, features. Is it conditions on transition points? Or some action space assumptions for the systems?
Yes, in the average reward setting, we have
You assume bounded reward?
bounded reward. Yes, that's enough for the discounted. For the average reward, actions are finite. States can be infinite. For the average reward, you're right. We have further assumptions. We make a bounded span assumption on the value functions. That's it. Thank you. Okay, let's move to the algorithm now. It's based on the linear programming formulation of MDPs. So remember that you can write our objective, the expected return, in these two ways. One using state action occupancy measures, and this will be the primal problem, and one using value functions. This is the dual problem. And the constraints in the primal, the constraint is just saying that your variable mu should be an actual occupancy measure. These are called flow constraints. And in the dual, you may recognize Bellman's equation in the form of a constraint. And these are linear programs, one in mu, one in v, and they're really one the dual of the other. If you solve these, of course, you need to know the transitions and the rewards to solve this, but then you can retrieve the optimal policy. There is a big problem, though, and this is that the number of variables and constraints scale with the number of states, which we cannot accept because we can have infinite states. But there are some ways around this. The first idea is this relaxed linear program. So the first step seems a bit weird, is to introduce like a mirror image, a copy of mu that is set equal to mu in this constraint. So it's really just a copy of the state occupancy measure. But something interesting happens in the dual. Now with this new constraint, the corresponding dual variable is now the Q function. So now you have both the V and the Q function. And now in linear MDPs, remember the reward and the transition are linear in these features. Big phi is just the feature matrix. I've just substituted the linear expressions in the primal program. But now you can do this variable, this change of variable, introduce this lambda. This is phi transpose u, and this is d-dimensional. So it's like we have removed a variable that was very large, was x prime a, we have replaced it with a d-dimensional variable. Also remember, in linear MDPs, the Q functions are linear in the features. So in the dual, now we have replaced the Q function with its d-dimensional parameter. And in linear MDPs, this still allows you to retrieve the optimal policy. Of course, we still have these other variables that are very large, but we will see how to deal with those. So from these, of course, you still need to know these unknown parameters of the MDP to solve your problem. But these programs gives us an idea for a learning algorithm that is to write the Lagrangian of these programs and then find the saddle point by gradient descent and gradient descent ascent. The challenge to do so is to obtain unbiased estimates of the gradients of the Lagrangian and also estimates with small variance from the data that we have. Yes. Oh, sorry. Yeah, capital E is just an operator that is summing over actions or copying values over actions. E transpose sums over actions, E copies values over actions. It's just to make dimensions match. Yeah.
You still have the U and V variables, and they are pretty large. So
yeah. So we will see soon that there is a trick that allows you to compute these variables in closed form to implicitly solve for these variables. We'll see this. Okay, this Primal-Dual approach was used in previous work by Gergely and Neckar for planning with a generative model. So in this setting, you can query for each state action that you want and get a reward and a next state. We want to do something similar, but in this offline RL setting, where you cannot query, but you have this fixed data set. And this requires one further trick. Again, a change of variable. Now, if I replace my lambda, that is this d-dimensional variable that replaces the state occupancy measure. So if I substitute it with the lambda to the 1/2 times beta, beta is my new variable. Lambda is the feature covariance matrix under the behavior policy. Now, if I do this substitution, I obtain a new primal program. And if I now write the Lagrangian, so I've reported it here, but details are not too important. What is important is that if now I compute the gradient, let's say with respect to my new variable beta of the Lagrangian, now it is easy to define a gradient estimate based on data that is unbiased and also has a small variance. Of course, now you can see this gradient estimate depends on lambda, so I need to know this matrix lambda to compute the gradient. But this is a requirement we can remove later, not for free, but we can remove it. Okay. Yes.
Yeah. To appreciate these, how would the gradient look like without this transformation?
Right. Okay. I don't have the expression here.
I would have thought that it's just a transformation with square root of lambda here and there appearing, because it's like they're linearly related, right? The two variables. So if you compute the gradient of one, then you square root lambda, multiply it, you should get the gradient of the other.
Right. So So one way to appreciate this is if you compute the expectation of this gradient estimate under your behavior policy, now you will get one lambda from computing this expectation that will give you, with this lambda to the minus 1/2, will give you this lambda to the 1/2 that appears in the actual gradient. I don't know if this gives more insight.
We don't know lambda. We
Um,
will estimate it, but sure.
yeah, this is if you don't know lambda. There is a version that you can.
But it seems to me that
if you know lambda.
anyways, maybe I just take a look later.
Okay. Maybe we can have a
I
closer
didn't
look.
appreciate it. It's just that I was curious.
Okay. There is still one big issue that are these, as Johannes was saying, there are these two variables that are still very large, right? Gradient with respect to theta, similar story. I don't have it here, but very similar story. So what do we do with these two variables? So we can use this trick again from previous work by Neka and Gergely. We can implicitly define these variables in this way. So both these state occupancy measure U, this will depend on your current policy and on your beta parameter. The V will depend again on your policy and on the theta parameter. You can just at each iteration of your Primal-Dual method, you can just plug these definitions of U and V. So you eliminate these variables and obtain this new function of beta, pi, and theta. It's no longer a Lagrangian, but everything still works. And basically you can so assigning these values to U and V still allows you to solve the problem.
So just
Yes.
to go into that a little bit more, what do you need to do to actually? I'm guessing this BOX you compute for the state you're in now. So this is local.
Yes. Oh, thank you. This is a very important point. So you don't need to compute the whole U for all state and actions and the whole V for all states. You can do this on demand. So for the states and actions that appear in your data, you can compute these values of V and U that you need. This is very important. Thank you. Because otherwise, still if you had to compute this whole vector V, still the computational complexity would be crazy. Yes.
Can we take a look at where U and V appeared previously in the expressions?
Yes. For instance, when you compute the gradient with respect to beta, you need to compute the V of X prime, so the next state in your data sample. Oh, here.
I see.
Here, for instance.
Yeah. The sample phase expressions only involve U and V as the data.
Yes.
And just you don't need to minimize with respect to U and V, do you?
You don't need no. You just plug these values.
So you minimize at theta and beta.
Yes, exactly. So our variables now are primal variable beta, dual variable theta, and you have to keep your policy up to date also. Now I tried to simplify the algorithm enough to put it on one slide. So this is a bit poor of details, but I hope it's understandable. So remember, the input is this data set, but now you go over the data set in an iterative manner, and it's a double loop algorithm because it has this inner loop where you do several steps of gradient descent on your theta, the dual parameters, and then you average these iterates. And on the outer loop, you do stochastic gradient ascent on your primal variable beta, and the policy you keep up to date, and it's a softmax with respect to the sum of your Q functions, because remember this linear combination gives you Q functions. So in a polytext style.
Sorry, should you remind us what was? That is basically the parameters of Q function.
So beta has replaced the occupancy measure, the primal variable.
Okay. What do we use beta for here?
Okay, yeah, you will need so you will need beta. Sorry, yeah, to compute the gradient with respect to theta, you will need beta. Okay. Sorry.
Okay, never mind. Sorry, carry on.
Okay. Okay, and now once you have processed the whole data set, you will just pick one of these policies uniformly at random.
Why do you need the averaging sort of iterative averaging for beta?
Okay, so the easy answer is since we have removed the state occupancy variable, we've replaced it with this low-dimensional beta, we can no longer retrieve policies from state occupancies. We need to retrieve policies from value functions. And so now, so let's say you need this inner loop, you have to think of it as a policy evaluation step. And you need this policy evaluation step to be accurate enough to compute your updated policy. Now, this is the easy answer. For the more complete answer, we will have to look at the proof, but I don't think there's time.
Sorry, so why is averaging helping? Is the I think averaging when I think convex plus noise.
Okay, why is averaging helping? So,
why is it necessary?
yeah, what is necessary is to do several steps of this theta update for each update of your policy.
Maybe this is the reason you get epsilon to the -4.
Exactly, yes. This is exactly the reason why we have epsilon to the -4 and not epsilon to the -2. Yes.
Could you expand on that?
Well, I mean, like it's just slow algorithms, defining variance, so you have to kind of collect more data, right?
Sometimes it's average was improved because of quality.
Be very up.
The average was improving in terms of the regret of pilots. So it's been surprising that it must get worse.
It's worse because of the double loop structure. It's worse than other offline RL methods.
You can take it.
Isn't this just like when you do Primal-Dual cycle point optimization, you can get these cycles, and you would need to do it at rate averaging to get rid of the cycles, which you don't have it in the convex optimization.
It's improved.
That's
right. So there's double average.
I'm not sure I got the question, but it seems Chaba has answered.
Oh, sorry. It was a question that if you have center point optimization, you can get this gradient descent.
Okay. Ah, yes.
Yeah, limiting behavior. And so one averaging is going to get you out of that, but I was just pointing out that that's the blue one.
The policy
Yeah.
policy update. Yeah.
That you're summing over all the previous
Yes.
value functions.
Exactly. Yeah.
That kind of breaks that cycle,
True.
but you still have the inside.
Yeah, and you still have this loop.
Yeah.
Also, the softmax is to make sure policies don't change too much from one iteration to the other. Okay, so this algorithm satisfies our requirements. It retrieves epsilon optimal policy with a polynomial number of samples. The rate is epsilon to the -4, so not optimal. The dependence on the coverage ratio is also not optimal. It's not linear, but it's quadratic, again, due to the double loop structure. So probably if we can solve the epsilon, if we can bring it to epsilon to the -2, we'll also have a linear dependence on C. No dependence on the number of states. Instead, we have the feature dimension D, of course, and polynomial computational complexity. So satisfies all of our requirements. Also, if we look a bit closer at the computational complexity of previous methods for this setting, we can see that their complexity was super linear in the number of samples. So for each data you analyze, you do a super linear number of computations. In our case, it's just linear. And we have improved the rate, not to the optimal one, but better than previous work. Now, it's easy to adapt this to the average reward setting, which is surprising because usually it's not the case. Also, you can remove this requirement that you know by B, actually, that you know the lambda covariance matrix. Not for free, you will scale with a coverage ratio that is larger than the one I have defined before. And of course, the main direction of future work is try to achieve this epsilon to the -2 sample complexity. This is still open also for the previous application of this method that was planning with a generative model. That's all. Thank you. The preprint of this paper is online, and of course, I'm here for questions. And later, if you want to have a closer look, I'm around.
Very cool. Any questions?
So for the planning, do you also get epsilon for the 4?
Yes. Yes. Same issue, double loop.
Same issue.
Yeah. No, that's another interesting thing. Nothing in this algorithm is pessimistic, at least not explicitly. If you see some form of pessimism in it, please let me know. But I don't.
Very good point.
Yeah, good question.
So then, how do you explain the philosophical conundrum that we need pessimism to get C-star? But hey, here we go.
That's a very good point. So one of the appeals of pessimistic algorithms is this partial coverage.
No, it's gone. It's over. Unless.
Do you think the pessimism sort of implicitly there in your trinomial formulation? That if dual variables are like a lower bound?
I don't know. Maybe if you look at it close enough, you can see some sort. I don't know. Maybe
There definitely no confidence sets.
there are no confidence sets. No. You could argue there is regularization. Maybe you could see this as a form of. But if you really want to see pessimism into this, I guess.
One more.
Yeah, could you please go back to see where you use the definition of the C?
Yeah. Actually, I have it here also. C star. This is the definition that I gave. So optimal features and feature covariance matrix to the inverse. Yeah.
Well, there are further details for unknown lambda. I see.
You have lambda to the -2 instead of
Yeah,
-1.
tricky. Okay.
I don't know if we have time.
So how important is it that you have a fixed behavior policy? Like, what would happen if you just get tuple state action reward the next state?
Okay, so I don't think it's fundamentally hard to generalize to that. I think you would need to define coverage not with respect to a policy, but with respect to your data in some way. I'm not sure, but I think it would not be fundamentally harder.
All right. I think that we need to wrap